So in this session, I'll tell you about one of the application of AI ML in the field of 5G network. So the title of this presentation is Role of Hog Empowered Vehicular Ad-Hoc Network in 5G network. So this talk comprises of various technologies starting from network, that is 5G network, and one of the emerging paradigm like fog computing, and another advancement over the network field, that is vehicular ad hoc network, and artificial intelligence and machine learning. So I'll tell you how to integrate AI ML in this particular domain, and what are the research problems in this particular domain that we are going to discuss in this session. So here you can see these are the topics that we are going to discuss. I think there is some issue in the presentation. Okay, otherwise I'll open. Yeah, these are the topics that we are going to discuss. We'll start with the introduction of this topic. Then I'll introduce about the fog empowered vehicular ad hoc network. Then I'll tell you about various device association technique, which are basically three types that we are going to discuss. Then I'll tell you about roadside unit resource scheduling, followed by one of the advancement over the RSU resource scheduling, that is revenue based service management. Then we'll discuss about another research problem where AI, ML, or these fields, whatever I told, these are integrated. In that problem, there are variety of solutions are there. So we are going to discuss about dynamic resource orchestration algorithm, which is a very base algorithm for it. Then we'll discuss about the signal aware algorithm. Then we are going to discuss about the combination of these two algorithms, that is dynamic resource orchestration plus signal aware algorithm. Then we are going to discuss about dynamic resource management algorithm, which is performing better in comparison to these three algorithms. And I will also tell you if you want to perform the similar type of problem, if you want to solve this similar type of problem, what are the simulation setups and what are the parameters you have to take. That I'll discuss at the end, followed by conclusion and references. So Internet of Things, or you can say the field of cloud computing, is nowadays very emerging. And in order to find some meaningful information, the AI, ML, or if you want to predict the trend, that AI or machine learning is more important to determine such type of trend. So you can talk about the smart city application, or you can talk about smart healthcare or smart transportation. So we have a set of devices, or we call a set of objects, and these objects are heterogeneous in nature because every object is having different capability, and they have also different storage power. So computationally, they are not equally capable, or they cannot store much data equally. So we call them as a heterogeneous device. So these heterogeneous devices are connected in various applications like smart city or smart building or smart transportation or smart healthcare. And there are several types of protocols are also used, like Zigbee is one of the very popular protocol. Wi-Fi we know, and every day we are using Wi-Fi of our institutes or our organization, or whenever we are traveling, we are also using airport Wi-Fi or railway Wi-Fi. And we have Bluetooth, we have long-term evaluation, and we have 5G. So these are the various technologies, especially Zigbee, Wi-Fi, and Bluetooth. These are integrated from first generation to current generation, that is fifth generation. So in fourth generation, all of us are now in fourth generation. We are using 4G mobiles, although 5G mobile is introduced. But in 4G mobile, we have two versions. We have LTE, that is called as long-term evaluation, and we have VoLTE. So you can see in your mobile phone it is showing VOLT, right? So basically there is a difference between the LTE and VOLT. LTE was launched by Airtel company, and VOLT is launched by the Reliance Group, that is Geo, whatever we are using. If you have a Geo mobile phone, so it is showing VOLT. So we have two type of connections. Like if you talk about this meeting platform, I am connecting through my voice, as well as I am connecting through this particular presentation. Similarly, if you talk about a mobile device or smartphone, we are connected with, I can say, we are connected with voice. Okay, we are also connected with internet, right? So both things, data as well as voice, both are considered in LTE and VoLTE. But there is an interference in the case of LTE, which is removed in VoLTE. So in VoLTE, you can do both voice and data simultaneously without any interruption. Now, whatever data these devices are generated, where to keep this data? Because if you talk about your smartphone or you talk about your smartwatch, the amount of data generated from these devices are very huge, and device cannot store much data. Like if you talk about your mobile phone can store 128 GB of data. It cannot exceed that one, right? If you talk about your smartwatch, it is again storing very nominal amount of data. So in order to store this data or analyze this data using AI ML techniques, so we push all these data to cloud. And if you talk about India, if you go for the data centers where the data are stored, yeah, is there any question? Madhu Prakash sir? Okay, I think it is by mistake. Okay, so when we talk about the data centers where the data are stored, so these data centers are available in remote location. They are not available everywhere. Like if you talk about our country, then I can say the data are stored in either in Mumbai data center or in Hyderabad data center. If you consider Amazon cloud, so is if I say that all the data generated in our country need to be stored in either in Amazon, either in Mumbai server or in Hyderabad server, so definitely it leads to response issues. So when we go for cloud, irrespective of the location, whenever that you want to push your data, that is going to be stored in a location. Okay, that is going to be stored in the remote location, right, or these particular locations. So there is a high response time or high service time. So unnecessary delay we are facing when we keep your data in our data centers. But there are many applications are there which are delay sensitive applications. Delay sensitive application means, I can say, there are some application where you need to take immediate action. Okay. Or these applications are called real time application. Like you can see like cardiac arrest, or I can say heart attack. So these are very if you look into healthcare, they are delay sensitive. Okay, if there is a minor delay, then we can lose the life of the human being, right? So in such application, the delay, bandwidth, and congestions, these are need to be overcome, so that faster execution can be done or faster treatment can be done to the patients, right? So that's why data should not be stored in cloud. All the data should not push to the cloud. Like here you can see in this picture, irrespective of the device, when you talk about smart transportation, or you talk about a smart key, or aeroplane system, or telephone, or smart TV, smartphone, whatsoever may be, all these data are sent to the cloud either through a wired connection or through a wireless connections. So because of that, these devices are facing latency or delay issue, and bandwidth is over utilized, and as bandwidth is over utilized, the congestion will be there in the network. So this particular network where we push all the data to the cloud to perform any AI or ML applications or AI ML analysis using AI ML techniques, analysis using AI ML technique. So that is not a feasible solution. So in order to avoid this one, there is a new computing paradigm that is started. That is started by Cisco. in the year of 2012, we call that as a fog computing. So it is hierarchical and distributed structure. So hierarchical means it is just like a tree structure, and it is completely distributed. It is not located in a particular location. It is distributed over various locations. Okay. So why the fog is more popular? Because fog extends all the cloud services, let it be computation or storage, near to the device. So as the services are available near to the device or edge, or it is available very close to the device or end user, so the latency is reduced, or you can say bandwidth is now going to be properly utilized and congestion will be less. But these fog nodes, if you look into these fog nodes are having limited computational power or storage power compared to cloud. So what we'll do, like if these devices need, these IoT devices or sensors needs some kind of processing, okay, that processing can be done using fog nodes. So you can put your model in the fog nodes. Okay, in the model AI ML model can process the thing and return the result to the corresponding device. So earlier what happened? All these devices are dependent on cloud. But now, if your computational requirement is satisfied, then it is going to be executed in the fog nodes. If your computational requirement is not satisfied, then it is going to be sent to the cloud. So previously, all these are redirected to the cloud, but now there is a, you can say, a filtration layer where we can execute some of the applications or some of the tasks, and the remaining tasks will still go to the cloud. So all the traffics which are sent to the cloud, now it is divided to the fog nodes, and some traffic it is going to the cloud. So each and every fog node is having some computational power, and one fog node may interact with another fog node to share the resources, right? And they have transmission and receiving capacity to the cloud as well as to the devices. So in that way, all this two-level framework, this IoT cloud framework, is now split into three levels. One is IoT layer, another is fog layer, another is cloud. Now coming to a fog empowered vehicular network. So this comprises of two different technology. One is the vehicular ad-hoc network, where vehicles are having high mobility power, and fog computing, which brings the services near to the cloud. Okay, so these two are integrated together in fog empowered vehicular ad-hoc network. So the main challenges with respect to the vehicular ad-hoc network is the latency, bandwidth, and congestion, which I told you. Always it is desirable that every technology should give low latency, high bandwidth, and low congestion, right? Or no congestion, I can say. So here you can see I am considering a particular area, right? You can say in a smart city I am considering a particular area where these are the different heterogeneous vehicles, or I can consider these are heterogeneous objects. They are moving from one side to another side, right? If I consider this area, I can say, if I say this particular left side and right side, so one vehicle is coming from left and it is moving towards the right. Similarly, one vehicle come from the right side and it is moving towards the left. And these vehicles are having also some computational power. So as these vehicles are having some computational power, storage power, nowadays every vehicle is having a onboard unit, which we call as OBU. In onboard unit, radar is also there. In onboard unit, based upon the different features of the car, we have cameras, we have sensors, we have lot of devices. So these devices also can form what? The virtual machines. Okay. Or they can provide the resources, okay, to different customers. So earlier customer is requesting for resources to the cloud, right? Now the customer will make a request to the cloud, but cloud is connected to a heterogeneous network. Okay, as it is connected to the heterogeneous network, from that network it can get the resources and execute it, right? For example, the nearest unit of these devices is called as RSU. What is that? Is called as roadside units, and we have another unit that is called as high power node, or we call it as HPN. So RSUs may be connected to the HPN. Like here also you can see RSU is connected to the high power node, and all the high power nodes are connected to a centralized unit, and the centralized unit is connected to the cloud data center through internet. Okay, So whenever a customer makes a request to the cloud can utilize the resources available in a particular area to execute certain applications, right? Here in this case, if you see fog perspective, I can say these vehicles are considered as IoT devices, and these HPN and RSUs are considered as our fog nodes, and in the top layer we have cloud. So now, if you talk about device association technique, right? How to connect a vehicle with a network, right? You need a 5G connection or you need a 4G connections. Like our mobile, we are connecting to our devices, right? How frequently you be connected, how much data you require. For this, we need different type of machine learning models to find some kind of patterns, right? How much data you have used yesterday, how much data you are using today. So I can predict how much data you are going to use tomorrow, right? So as all smart vehicles establish a connection between the fog nodes to they are connecting with the fog nodes to provide the resources or they are requesting for some resources. So this happens with respect to the device association technique. Okay. So every device is connected to the network through a device association technique. So this device association technique is split into three parts. One is called as signal aware technique, content aware technique, and capacity aware technique. So signal aware technique means we consider the signal to interference plus noise ratio. So if signal strength is good, then I am going to connect that particular device. And some device may be in the overlapped region where they may be connected to more than one roadside unit or more than one high power nodes. Like whenever you are moving from one place to another place, so you can see towers are referred, right? Sometimes multiple towers are referred, or based upon the signal strength, one of the tower is referred out of all set of towers. So that is based upon the signal strength. That is called as SINR quality. Similarly, we have a content aware technique. In content aware technique, instead of checking the signal, we look into favorite content. For example, you want to download a video in GB. So your favorite content you can download in gigabytes, not in the megabytes or kilobytes. So that is your content aware techniques. Similarly, you can think about the capacity aware technique. So based upon the resources, computation, storage, we are going to provide the resources to the customer, right? Suppose a user requires computation only, so we can restrict it to computation. Suppose another user requires only storage, so we have to find the nearest available resources where storage can be provided. So now I am going to illustrate you a particular problem in the signal level technique. So before going to this one, you can look into this particular picture where there is a single network is there. Okay, network tower I can say, or I can say roadside unit, or I can say a high power node is there, and these one, two, three, whatever I represent, these are the vehicles. However, when a vehicle is close to a particular tower and its speed is more, right? If it is near to the tower, then the speed is 10 Mbps. But if it is away from the tower, like you can see, this is a place where it is little bit far from the tower, and this is also the same place, then it is 7 Mbps. Similarly, if it is again a little bit far, so it is 5 Mbps. Similarly, if you go a little bit far, then the speed is decreases and you will not get a signal from this particular tower. So like that, here you can see at time instance t is equal to 1. One vehicle enter inside the coverage area of this particular network. Okay, at t is equal to 1. But when I observe at t is equal to 2, the vehicle moved from 5 Mbps zone to 10 Mbps zone. So you can say the mobility of this vehicle is very high, right? And similarly, when I observe at t is equal to 3, okay, these are some regular intervals, or you can say equally distributed intervals. At t is equal to 3, I observe that this vehicle is available in this particular zone, that is 5 Mbps zone. And t is equal to 4, that vehicle is no more available in this particular network. Okay. So 5 Mbps zone, 10 Mbps zone, another is 5 Mbps zone, then it is gone, right? But when I observe the vehicle number 2 is available in the 5 Mbps zone, But in the next time instance, it is in the 7 Mbps zone. Next time instance, it is in 10 Mbps zone. Next instances, it is in the 7 Mbps zone. And next instance, it is in 5 Mbps zone. And t is equal to 7, it is outside the network. Right? So you can say the mobility power of vehicle 2 it is less in comparison to the mobility power of the vehicle number 1. Similarly, when we talk about vehicle number 3, vehicle 3 also entered to the network at this particular period of time, and it is slowly moving up to t is equal to 7, and when t is equal to 8, it is outside the network. So I can say the mobility power of the vehicle 3 and vehicle 2 is more or less same. Now, with respect to this, I am going to tell you a problem, and the solution to that particular problem is called as RSU resource scheduling, or we call it RRS. So our objective is a provider. Suppose I am a mobile provider, mobile service provider, or I am a network provider. So always I want to maximize my profit, right? So for example, if you look into this particular situation in this particular network, like t is equal to 1, okay, in our network only one vehicle is available, right? That is vehicle number 1. And how much that particular vehicle can download? The vehicle can download 5 Mbps of data. You can see if you are in 5 Mbps zone, you can download 5 Mbps. However, every vehicle has a requirement. So vehicle 1 requirement is that it needs to download 25 MB. Okay. Vehicle 2 requirement is that it is going to download 22 MB, and vehicle 3 requirement is that it is going to download 30 MB. And in order to go for the revenue model, so we consider that for MB you have to pay some amount. For example, I can say I can pay 15 per MB. Okay, if vehicle 1 agreed to pay 15 per MB, and vehicle 2 agreed to pay 35 per MB, which is very huge, and vehicle 3 is going to ready to pay 5 per MB. Okay, so what we'll do at t is equal to 1, only one vehicle is there, so we don't have any other option. When you have multiple vehicles, then you can think about which vehicle you are going to take. But here there is no multiple vehicles, so I am going to assign this particular slot to this particular vehicle. Okay, t is equal to 1 slot I am giving to vehicle 1, so it can download 5 MB, and it is ready to pay 15 per MB. So 5 into 15. 5 into 15 is 75. So vehicle 1 got 5 MB out of 25 MB, because in order to fulfill its complete request, it is we need to download 25 MB, and the prices is 15 per MB. Right? So it is paid. It has to pay 75 cost in it for booking the slot t is equal to 1. Now when you go for the t is equal to 2, in t is equal to 2 we have two vehicles. One is vehicle number 2, another is vehicle number 1. However, vehicle number 1 is in 10 Mbps zone, and vehicle number 2 is in 5 Mbps zone. So normally we have a normal convention that if a vehicle is close to the mobile tower, it is going to download more. So the chances of getting a connection is more. And if a device is away from the mobile tower, the chances of connecting is less. So let us see in this scenario. So here, if you talk about vehicle number 1, so it can download 10 Mbps at a cost of 15 per MB. So 10 into 15, so we'll get 150. And similarly, if you talk about vehicle number 2, it can download 5 Mbps at a cost of 35 per MB. So 5 into 35 means we will get a revenue of 175. Now we have calculated the revenue of vehicle 1, that is 150. The revenue of vehicle 2, it is 175. So now you tell me which vehicle is going to get t is equal to 2. Can anybody answer this question? If the revenue is 150 and 175 for vehicle 1 and vehicle 2, which vehicle you are going to allot t is equal to 2? Are you going to consider vehicle 1 request or vehicle 2 request? Okay, obviously you will go for vehicle 2 request because you are getting more revenue. Wherever as a provider, you need to maximize your revenue. So if you analyze this thing, then you will get 175, you are getting more revenue. That's why you are going to assign this particular slot to vehicle number 2, not the vehicle number 1. So you can see, not necessarily that if a vehicle is close to the mobile tower, it is going to get the service. Sometimes the if the device is very far away also, due to the vehicle is ready to pay more cost, so it is going to use that particular service. Now, when you go for t is equal to 3, if you go for the next scenario, t is equal to 3, here we have 3 vehicle, vehicle number 1, vehicle number 2 and vehicle number 3. So vehicle number 1, it is in 5 Mbps zone, vehicle number 2 is in 7 Mbps zone, and vehicle number 3 is in 5 Mbps zone. Okay. So if you talk about this 1, 2, 3 vehicle number, so here I can download 5 Mbps, but vehicle 1 is going to ready to pay 15 per MB, so it is 5 into 15. And similarly, vehicle 2 is available in 7 Mbps zone. Okay, so the cost will be 35 into 7, so you will get 245. Similarly, if you talk about vehicle number 3, vehicle 3 can download 5 Mbps, 5 Mbps, and it is going to pay 5 per MB. So 5 into 3, you will get 15. Okay, sorry, 5 into 5, you will get 25. So if you look into these 3 vehicles, the maximum revenue we are getting in the case of vehicle 2. So we are going to give vehicle 2, which requires 7 Mbps. We are not going to honor the request of vehicle 3 and vehicle 1. Now if you talk about vehicle 2 has downloaded 5 Mbps here, and it has downloaded 7 Mbps here, 5 plus 7, right? 5 plus 7, that is 12 MB. And vehicle 1 is vehicle 1 has downloaded how much MB? Vehicle 1 has downloaded only 5 Mbps. So this is the scenario up to t is equal to 3. Now when you go for t is equal to 4, now 1 is out of order. So 1 is able to get only 5 MB out of 25 MB. So it is requested 25 MB, but we can only provide 5 MB. Okay, we are not going to provide 25 MB because its requirement is not satisfied based upon our revenue model. Okay, now t is equal to 4, you have vehicle number 2 and vehicle number 3. Vehicle 2 is present in the 10 Mbps zone, and vehicle 3 is available in the 7 Mbps zone, right? So you can see that it can download 10 Mbps and it is ready to pay 35 per MB. So we are going to get 350. However, if you talk about vehicle 3, it can download 7 Mbps and it is going to pay 5 per MB, that is 7 into 5, that is 35. So now if you look into this scenario where you are getting maximum revenue in the case of vehicle 2. So I am going to assign to vehicle 2. Okay, and you can see vehicle 2 requires maximum of 22 MB, and it is downloaded 5 MB here and 7 MB here and 10 MB here. So 5 plus 7 plus 10, so it is downloaded 22 MB. So that's why I am saying vehicle 2 requirement is now fully satisfied. That means at t is equal to 5, t is equal to 6, although vehicle 2 is there in the system, it is not going to download anything because it has already its requirement is satisfied, right? Now coming to t is equal to 5, here vehicle 2 requirement is satisfied, so only vehicle 3 is there, so it can download 10 Mbps at a cost of 5 per MB, so it is downloading 50. Similarly, when you go for t is equal to 6, we have vehicle 3 only, vehicle 2 is requirement is satisfied, so vehicle 3 can download 7 Mbps, 7 into 5. Okay, 7 into 5 per MB, so it is going to download 35 MB, right? So till now, if you see, vehicle 1 got only 5 MB, vehicle 2 got 22 MB out of 22 MB, and vehicle 3 got a slot here, that is 10 Mbps, and here 7 Mbps. So total it is downloaded 17 MB out of 30 MB, right? Now when you go for t is equal to 7, so here vehicle 3 can download vehicle 3 can download 5 Mbps, right? So at a cost of 5 per MB. So it is 5 Mbps and 5 per MB. So we can download 25. 5 into 5 means 25. So we have to pay 25 for downloading 5 Mbps. Okay. So vehicle 3 is to pay 25 Mbps. So 25 rupees or 25 cost unit. And its whole requirement, if you see, earlier it is 17 MB, but here it is downloaded 5 MB. So 17 plus 5. So total 22 MB it is downloaded out of 30 MB. So in this way, actually RRS scheduling algorithms works. And if you see the total revenue we got is, you can say 75 plus 175, 245. You can add this one. You will get the total revenue received by the network provider from various vehicles is 955. And now question arises that can we apply some kind of techniques, okay, to reduce uh, the cost of all the you can reduce the cost of all the users, right? Network provider side, always you want to maximize your profit, but if you look into the user perspective, user always wants to minimize the cost. So if you can design a particular model using same scenario where the cost is less than 955, you can apply AI, ML or any technique, right? If you can do it, then obviously people are going to use that particular model, right? So I am showing you another example of RRS. So in this case, you can see again vehicle V1 is a very fast vehicle. So here I have taken four different zones. One is 2 Mbps zone, 3 Mbps zone, 4 Mbps zone, 5 Mbps zone, again 4 Mbps, 3 Mbps, and 2 Mbps zone. So you can say the mobile tower is here in 5 Mbps zone, right? If you are away from the tower, then the speed decreases. Similarly, you can see V2 is little bit slower vehicle than V1, but faster vehicle than V3. And again, every vehicle has a request and it has a price model. For example, vehicle 1 wants to request 8 MB and the price is 10 per MB. And vehicle 2 also request 10 MB, request 10 MB and at a price of 30 per MB. Similarly, vehicle 3 request 22 MB and the price is 5 per MB. So in this case, if you see at t is equal to 1, there is only one vehicle, that is B1. So it can download 3 Mbps and we are ready to pay 10 per MB, right? So the revenue cost, the revenue that generated using this particular vehicle is 30. Okay, the vehicle has to pay 30 cost units to the network provider. But when we go for t is equal to 2, here you can see there are two different vehicles we have. One is the vehicle V1, another is the vehicle V2. So V1 can download 5 Mbps and V2 can download 2 Mbps. As V1 can download 5 Mbps, so 5 into 10. So we can get this 5 Mbps at a cost of 10 per MB. So revenue is 50, right? But when you go for this V2, V2 can download 2 MB at a cost of 10 at a cost of 30 per MB. So 2 into 30, right? 2 Mbps into 30 per MB. So we are going to get revenue of 60. So till now, if you can see, vehicle B1 got a request here, and its size is 3 MB, and vehicle 2 has a request here, so that is 2 MB. Right? Vehicle 2 has a request here, that is 2 MB it can download. So vehicle 1 got 3 MB out of 10 out of 8 MB, and vehicle 2 got 2 MB out of 10 MB. Now, if you talk about T is equal to 3, here you can see I have three vehicles, V1, V2, and V3, and they are available in 3 Mbps, 4 Mbps, and 2 Mbps zone. So, if you talk about 3 Mbps zone, okay, 3 Mbps zone, it can in this particular zone you can download 3 Mbps, but the cost is 10 per MB, so revenue is 30. But if you look into here, here you can download 4 Mbps. That means vehicle V2 can download 4 Mbps, and the cost is 30 per MB, so revenue is 120. Similarly, if you go for V3, okay, V3 is available in 2 Mbps zone, and it can download 5 per MB. So 2 into 5, it is going to be 10. Okay. So if you consider this particular situation, okay, if you see the total this particular solution, so we have three slots, right? T equal to 1, T is equal to, T is equal to 3. Again, three slot, we have three different vehicles, but maximum revenue we are getting is 120. That is in the case of vehicle 2. So we will honor the request of vehicle V2 and reject the request of V3 and V1. So it is going to download 4 Mbps. Earlier it got 2 Mbps here. So 2 plus 4, it is 6 MB, and vehicle 1 case it is 3 MB. Right? So the total revenue we got in this case is 120, and you can say if you want to calculate cumulative one, then you have to add T is equal to 1, what is the cost, T is equal to 2, and what is the cost, and T is equal to 3, what is the cost, and sum all these values. Then coming to T is equal to 4, here you can see there is only two vehicles. One is vehicle V2 available in 4 Mbps zone. Vehicle V3 is available in 3 Mbps zone. Okay, so 4 Mbps at a cost of 30. So 4 into 30 you will get 120. And V3 case it is 3 Mbps at a cost of 5 per MB, so it is 15. So out of these two, the maximum one is 120. So we are going to accept the request of vehicle 2 and reject the request of vehicle 3. So if you sum the if you calculate the overall download by vehicle V2, so it is earlier 6 plus now it is 4. So 6 plus 4, it is 10 MB. So its requirement is 10 MB. So now vehicle 2 also downloaded at 10 MB. So its requirement is satisfied. So vehicle 2 is not going to participate at T is equal to 5 because its overall requirement is satisfied. Okay, now if you go for this particular situation where T is equal to 5, although we have two vehicles, as I mentioned, vehicle 2 requirement is satisfied, so vehicle 3 request is only going to be considered. So vehicle 3 can download 4 Mbps, right? Vehicle 3 can download 4 Mbps, and it has to pay 5 per MB. So 5 for into 4, it is 20. So here the revenue is 20, right? So now the vehicle 3 downloaded only 4 MB out of 22 MB, and vehicle 1 downloaded 3 out of 8 MB, and vehicle 2 requirement is fully satisfied. So when you go for T is equal to 6, again here you can see T is equal to 6, only one vehicle is there, that is V3. It can download 5 Mbps at a cost of 5 per MB, so 5 into 5 you will get 25. Okay, you will get 25. So now the cumulative download by vehicle V3, earlier it is 4, now I have added 5. So 4 plus 5, it is 9 MB. Now proceed further at T is equal to 7, only vehicle V3 that is available in 4 Mbps zone. So 4 Mbps at a cost of 5, so 4 into 5, it is 20 per MB. Similarly, when you go for T is equal to 8, T is equal to 8 case, we can download 3 Mbps and at a cost of 5 per MB. So 3 into 5, it is 15, right? But the cumulative download by vehicle V3 is 13 plus 3, it is 16 MB. Anyhow, it requires 22 MB. So we'll proceed for T is equal to 9. In T is equal to 9, V3 can download only 2 Mbps. Okay, at a cost of 5 per MB, 2 into 5, it is 10. Okay. So total revenue in this particular case it is 10, but vehicle 1 is able to download only 3 out of 8 MB, whereas vehicle 2 can download 10 out of 10 MB, so its requirement is fully satisfied, and vehicle 3 can download only 20 to 18 MB from 22 MB. So this is the performance what we achieved in the RRS, and if you calculate the total revenue in this particular case, if you sum T is equal to 1 to T is equal to 9, all the time slot if you add, then you will get the grand total revenue is 420. So if you can develop a algorithm where the grand total revenue is minimized, but definitely the user cost is saved, right? Although provider is not in profit, but we have to look into the user perspective also, because there are some developments we are doing from the user perspective, there are some development we are doing from the provider perspective, right? So our objective is to minimize the total grand total revenue. So for this, there is an algorithm called revenue based service management, that is RBSM. We suggest that instead of taking these vehicles decision by calculating how much data they can download and what is the cost they are ready to pay, we need to sort the vehicles in the order of how much they are going to pay per MB. For example, you can see vehicle 2 can pay 30 per MB, that's why I put vehicle 2 first, and vehicle 1 can put in second because it can download 10 per MB, and vehicle 3 can download 5 per MB, right? So vehicle 2 followed by vehicle 1 followed by vehicle 3. So now, as vehicle 2 provides maximum, vehicle 2 can download the maximum. If vehicle to download more MB, then it has to pay more, right? So what we'll do, we'll only focus on the vehicle 2 first, because if we give more slot to vehicle 2, then we get more revenue, right? Okay. So you will get more revenue if more slots are given to vehicle 2. So we focus on only vehicle 2 slots, and we found that vehicle 2 is available at t is equal to 2, t is equal to 3, t is equal to 4, and t is equal to 5. Okay, because other slots it will be out of order. So now instead of taking it t equal to 2, t is equal to 3, 4 and 5, we do the reverse order. The reason is that before t is equal to 5, your requirement need to be satisfied. Okay, but after that the vehicle is not available. So instead of going for t is equal to 2, t is equal to 3, 4 and 5, what we did? We go for 5, 4, 3, 2. Okay, in 5 it can download 2 Mbps, and 4 it can download 4 Mbps. So cumulative is 2 plus 4, that is 6, and requires 10, right? And here it can download 4. So 2 plus 4 plus 4, so it can download 10. So its requirement will be satisfied, and there is no need to assign any resources to vehicle 2 at t is equal to 2. So it can download at t is equal to 3, t is equal to 4, t is equal to 5 in the reverse order. Okay. The total download is 10 MB and it is ready to pay 30 per MB. So 10 into 30, so it is 300. So total revenue generated by this RBSN algorithm is 300. Right? Now once vehicle 2 requirement is satisfied, we can go for vehicle 1. When we go for vehicle 1 is available at t is equal to 1, t is equal to 2 and t is equal to 3, but it is not available here. Okay, vehicle 1 is available at t is equal to 1, t is equal to 2, t is equal to 3, but it is not available at t is equal to 3. Right. So why it is not available? Because V2 has already taken the t is equal to 3, so it is not applicable. But it can download only 5 Mbps here, it can download 3 Mbps here, so 5 plus 3 it can download 8 Mbps. Okay, it can download 5 Mbps here and 3 Mbps here, so together it is 8 Mbps. So 8 into 10, so we can expect a revenue that vehicle 1 has to pay, that is 80. Okay, that is 80 it can generate to the revenue. Okay, so vehicle 1 occupy the slot 1 and 2, and vehicle 2 occupy the slot t equal to 3, 4 and 5. So vehicle 3 can occupy only slot of t equal to 6, t is equal to 7, t is equal to 8, t equal to 9. Other slots are booked by other vehicles. So total what we can get, it is here 80 MB and there we got to 300 MB. So total it is 380. Now coming to vehicle number 3. Vehicle number 3, we can provide resources at t is equal to 6, 7, 8, 9 in reverse order. So it is 2 plus 3 plus 4 plus 5. So 2 plus 3, 5, 5 plus 4, 9, 9 plus 5, 14. So we can download 14 MB at max out of 22 MB. So 14 into 5. So we can pay 14 into 5, that is 70. Okay. So earlier it is 380 Okay, because vehicle 2 got will provide the revenue of 300 MB. 300 is the revenue, and vehicle 1 can provide vehicle 1 can provide 8 into 10. Okay, so it is 80, and in this case it is only, I can say, how much? It is 14 into 5, so that is 70. So together we have a grand total revenue of 450. But if we go back to this slide, here you can see total revenue is 420. So if you go for provider perspective, okay, if you go for provider perspective, who is better? Provider perspective, RBSM is better, right? So if your objective is to maximize that grant revenue, RBSM is providing better. But if you look into user perspective, then obviously RRS is better. So in this case, I think it is we have considered that maximize the grand total revenue. Earlier I told you minimize the grand total revenue, but it is actually maximize the grand total revenue. So earlier we have in the case of RRS algorithm we have 420, but here the revenue is increased to 450. So obviously RBSM algorithm is better in comparison to the RRS algorithm. Okay. So if anybody is having any question, you can ask before proceed to the next problem. Anyone having any question in RSU based resource scheduling and revenue based service management, you can ask. Yeah, any question, anyone? Okay. So if there is no question, I will go for the second problem. So in this problem, you can see these are the different fog nodes, right? I have represented by fog node 1, and this I have represented by fog node 3, this is fog node 2, and this is fog node 4. So you are given with a fog empowered vehicular radar network in which a particular city, if you consider this is a part of the city which we divide into different zones. Okay, and we deployed f number of fog nodes in this particular zone, and each fog node is having a communication range which we represent with this dotted circle, green color dotted circle, and you can see one circle is overlapping with another circle. That means I can say one fog node to communication range is overlapping with its neighboring fog nodes communication range. Okay, so you can see the vehicles are moving from one region to another region. Okay, for example, I can say you like this particular vehicle earlier it is maybe in fog node 4, and now it is moving towards the fog node 1. Okay, and a particular fog node provides services to set of vehicles. Like here I can say, if we talk about fog node 1, fog node 1 provides services to vehicle 7, it is providing services to vehicle 4, it is also providing services to vehicle 2 and vehicle 1 as well. So it can provide services to multiple vehicles, right? So, but although a vehicle maybe like if you talk about vehicle V1, it is in the range of fog node 1 as well as fog node 4, but finally it is going to get services from only one fog node. It cannot get services from multiple fog nodes, right? Okay, so now in a particular network, when we consider a network, if you want to do some kind of analysis, then I can say the vehicles may arrive and departure from a particular network. Like if I consider this a network, many vehicles are entering this network and many vehicles are departing this particular network. So I represent the mean value of this arrival rate in the network is lambda, and we consider the departure rate of the vehicles from the network by mu. Okay, this is required for experimental purpose because in a particular network, number of vehicles may enter a network is quite more in comparison to number of vehicles leaving the network. On the other hand, I can take a scenario, number of vehicles entering the network is equal to the number of vehicles leaving the network. On the other hand, I can take a typical case where number of vehicles are leaving the network is more in comparison to the number of vehicles entering to the network. So in that case, you can consider the number of vehicles that are available in a particular network is quite more. Okay, there are some vehicles already there, they are leaving more. Right? And you can see there is a particular number. In this picture, you can see some number is written. If you look into this particular number, we call that number as a resource block. Okay, if I go for resource block of IK, it indicates that the total number of resource block required for kth vehicle with data rate dk from ith node, ith fog node. So I represent the fog node, K represent the vehicle. So resource block required for a particular vehicle with a data rate dk. Okay, from a particular fog node that is represented as RBIK. And obviously, it is possible when a particular vehicle is present in the coverage region of a fog node. Otherwise, it is not possible. So resource block of IK is represented as ceiling of 1 by B. B is the bandwidth. Log base to 1 plus SIK. SIK represents the signals between the ith fog node and kth vehicle. So this is a signal level approach. I told you in device allocation technique, we have three types of approach: signal aware approach, context aware approach, different approaches, right? So here we particularly focus on the signal aware approach, and we multiply with dk. So the dk is nothing but the data rate of the vehicle k. Okay. So these vehicles, these values are easily predetermined so that you can easily understand. And the number of vehicles connecting to the fog nodes increase rapidly over time. So we know that if you consider from night 12 to morning 12 or 12 noon, so you can see as the day progress, the number of vehicles entering to any particular area is increasing. Okay, and sometimes every fog node is having a limited capability, so it can adjust the capacity of the fog node. Every fog node has a capacity, so if more vehicles are coming, definitely the vehicles who arrived late, they are not going to get the services. Like if you talk about a parking lot, in a parking lot, let's say 100 vehicles can be parked, but let's say there are two vehicles are coming to that particular place. So first 100 vehicles are going to get the service, rest 100 vehicles has to wait. Okay, and sometimes also network is going to be important to provide the services because there is a limited resource constraints. And the new incoming vehicles connect to the fog node that own inadequate resources. So we have to think that how to manage this network in such a manner that even if even if there is a even if you can say if you look into a particular network, if you manage the resources in a nice way, then if more vehicles are coming, then definitely.
Not half the way this is all going horribly wrong. Can I cancel the wedding? Is that going to ruin it?
Any question?
Okay, let's try this again. There's a heat wave starting on Tuesday, so even though this is only going to give us like 24 hours to play.
Okay, so if the new vehicles are accommodated, it is going to be accommodated in the network. Then you have to manage the network in a by applying some well-defined approach, so that you can minimize the resources or something like that, right? So obviously, the solution is that the services of the vehicles are migrated between pairs of the fog node without increasing the number of resource blocks. Okay, like if a vehicle is getting services from two fog nodes, then we will see which fog node is consuming less resources. Okay, which fog node is providing better quality of resources, which fog node is not spending much time. So based on different factor, energy may be factor, delay may be factor, bandwidth may be factor, congestion may be factor. By looking into these factors, we can take a decision. So our objective is to maximizing the resource block reduction. We have to reduce the resource block so that number of vehicles getting services is more, and we have to maximize it, right? So now, if you see, there are certain performance matrices are uh, used to calculate the performance of a particular network. So their objective is also need to be maximized. Like network service capability is maximized, network serviceability is maximized, network availability is maximized, network throughput is maximized, and resource utilization efficiency is also maximized. Now, if you look into these parameters, I'll show you the definition of these parameter. For example, if you talk about service capability, it is the ratio between the remaining resources and total number of resources in the network. So, for example, in a particular network, you have 10 resources or 10 instances. Out of 10 instances, 7 instances are remaining. So, remaining instances is 7, total is 10. So, 7 divided by 10 is the network service capability. Similarly, when you go for network serviceability, it is a percentage of vehicles getting served with desired requirement in the network. Like somebody can say that, like whenever you are watching a YouTube video, you can say that I want to see this video with 1080p or 720p. So that is your desired requirement. So still, if the network is poor, you are not going to get your service with 1080p, or you are not going to get the service with 720p, right? So in that case, your desired requirement is not satisfied, right? So you maybe provide the service with minimum requirement. So minimum requirement may be 144p, right? But we are looking into how many vehicles are getting the services by fulfilling the desired requirement. The percentage of vehicles. Suppose 100 vehicles are there, and let's say 30 vehicles are uh, getting their resources with the desired requirement. So I can say percentage of vehicles is your 30%. Similarly, but if you go for network availability, it is the percentage of vehicles getting served with minimum requirements in the network. So, for example, 100 out of 100 vehicles are getting services with minimum requirement, but 30 vehicles perform with desired requirement. So, I can say 100% is the network availability, because those vehicles are fulfilling the desired requirement, they are also fulfilling the minimum requirement. Similarly, we have network throughput. Network throughput, it is nothing but it is obtained using vehicles achievable rates at a different time slots and from different fog nodes. So it is directly proportional to the time fraction allocated to the vehicles getting the services. So throughput means you can say how many service requests you are fulfilling with respect to a time frame. Let's say 100 vehicles are fulfilling their requirement per minute. So I can, based upon that, I can calculate what is the throughput of the system. Similarly, we have resource utilization efficiency. It is the percentage of occupied resource blocks in a network. So if the all the resource blocks are fully occupied, then I can say 100%. So resource utilization efficiency says that how much of resources is properly utilized, right? Obviously, in computer also utilization, right? So I can say the processor is fully utilized, then 100% of the processor is utilized 10%. So it is a poor utilization. So these matrices will help you to determine the performance of the algorithm. So I'll tell you four different algorithms, starting from the first algorithm, that is called as dynamic resource orchestration algorithm. So in short, we call this algorithm as a DRO algorithm. So let us understand how it provides solution, how it maximizes the reduction of the resource blocks. Like here, you can see I am taking, I think I am taking here 10 vehicles, okay, V1 to V10, and I am taking four different fog nodes. Like if you talk about this fog node 1, the fog node 1 is this is the coverage range. In its coverage range, four vehicles are there. Out of these five vehicles are there. Out of five vehicles, I can say two vehicles are in the overlap region with FN4, and two vehicles are overlap region with the FN2, right? So these vehicles which are in the overlap region, they will get either a service from fog node 1 or they will get a service from fog node 2. They cannot get service from both the nodes, right? So now, for example, here you can see I am representing two different lines. One is a dotted line, another is a dashed line. Okay. So you can see, like if I say FN1 and FN2, right? So dotted line is the line in which a vehicle can be connected to another fog node, but it is not connected now. But solid line indicates that the vehicle is now getting services from that particular fog node. For example, when we talk about the pair of fog node, I can take a pair Fn with Fn2, I can take Fn1 with Fn4. I cannot take Fn1 with Fn3 because there is no overlap between these two. Okay, so we represent this particular problem as a graph modeling problem. Okay, we represent it in the form of a graph. So you know, graph is nothing but a set of vertex and set of edges. So I represent each and every fog node as a node. We represent each and every fog node as a node in the graph, and the overlap between two different fog nodes in the form of edges. So I represent in the form of resource blocks. So for example, if you look into fog node 1 and fog node 4, or fog node 1 with fog node 2, how much resources is going to be reduced? Resource blocks are reduced. That is represented here. How to calculate this value? That I will tell you now. So if you talk about the fog node 1 with fog node 2, you can see there is two vehicles. I am not considering the vehicles that are explicitly in the range of fog node 1. If a vehicle is in explicit range of FN1, that I am not considering. So if you consider these two overlap vehicle, like this particular vehicle is getting service from this fog node 1, that is 516, and this vehicle is getting services from fog node 2, so that is 421. So currently it is consuming the number of resource block is 516 plus 421, so that is 937. But this vehicle can get a service from FN1, and similarly this particular vehicle can get service from fog node 2. So if they do like this, then the number of resource block is 315 plus 327, and 315 plus 327 is 642. So if you see, the number of resource blocks reduced here is 937 minus 642, it is 295. Similarly, if I go for the pair between Fn1 and Fn4, so in the previous one you can see, if I go to the previous one, yeah, the number of resource block reduced is 295, which I represent in the form of a graph. Now, in the case of Fn1 to Fn4, if you see Fn1 to, again two vehicles are there. Okay, so currently if you add the solid line values, that is 260 plus 682, you will get 942. But they can get the service like in what is given in the dotted line. So if they go for dotted line, then it is 412 plus 213. So it is 625. So number of resource block reduced is 942 minus 625. So we will get the value as 317, which I have represented here. Okay. Similarly, what I can do, I can take fog node 4 with fog node 3. So there is only one vehicle here, and solid line represent 256. So instead of that, if you take the dotted line, that means the vehicle is connected to FN4, so you will get 126. So 256 minus 126, you will get the value is 130, which is written here. Now we are left with only one pair, that is FN2 to FN3. So again there is only one vehicle. So if I take the solid line, the number of resource block is 486. But here in the dotted line, the number of resource block is 238. So 486 minus 238. So number of resource block reduction is 248. So now what we will do, you got in each and every pair how much the resource blocks we can reduce if we go for the solid dotted line instead of the solid line. So But if you go for maximum weight matching, which is used by this DRO algorithm, so you cannot take all these reductions. It says that find the maximum resource block reductions. So if you compare 130, 317, 295 and 248, the maximum resource block reduction is 317. Okay. So you have to take the first one is FN1 to FN4, right? And if you are choosing FN1, FN4, as it is based upon the graph coloring problem, and we know in graph coloring problem, if you assign a particular color to a node, its neighbor should not be get the same color, right? So, uh, so if you are choosing FN1 and FN4 pair, then you cannot choose the pair of FN1 and FN2, and similarly you cannot get the pair of FN4 and FN3. So the thing is that we can only choose a pair that is in between FN2 and FN3, right? So in this case, if you are selecting 317, then you have to select a 248. You cannot choose both, right? So 37 plus 248, if you sum it, I think it will come. I have added here, I think. Yes. So the maximum number of resource block you can reduce by the help of DRO algorithm, it is 565. Okay. But we are not considering the resource block reduction between FN1 to FN2 and FN4 to FN3. The reason being why it is not considered is that due to the graph coloring problem. In graph coloring problem, we are not going to choose the adjacent nodes with the same color. That is the reason why these two pairs are not considered. Now, in order to avoid this one, there is a popular algorithm that is called as signal aware algorithm. In signal level algorithm, we have macro base stations, we have pico base stations. Okay. So what is macro base station? What is pico base station? That I will tell you here. Like here you can see these are called as macro base station, and in this network, which we call as a het net. Het net means it is a heterogeneous network. So there is two tier here. One is one tier you have macro base station, another tier we have pico base station. Okay. So there is two macro base station here. You can see this is the one macro base station. This is another macro base station, and there is two traffic hotspot. These are the two traffic hotspots in which we have pico base stations. Okay, these are also pico base stations. So each hotspot is having three pico base station, and the whole heterogeneous network is having two heterogeneous. In the heterogeneous network, you have two macro base station. Now let us understand the concept between these two base stations. So here you can see in the picture there is a time frame, I can say 1 minus a. There is another time frame that is a. So in 1 minus a zone, okay, you can see the macro base station is active. So once the macro base station is active, the pico base stations are not doing anything. So a macro base station is periodically mutes during the so-called almost blanking subframes to mitigate the interference to the small cell users. So here the macro base station is active, whereas in this particular time slot, the macro base station is not providing services. So you have to get services from the pico base stations. So if I consider there are I number of let's say slices are there. So this macro ABS is now divided into L number of slices. So 1 minus A in the case of macro base station is referred first. If macro base station needs help, then we can go for pico base station. But first is macro base station. But in A, this A zone will only consider the pico base station. That's why for that we are dividing it into I number of slices. And within each slices, that is A1, A2, A3 up to AI, a set of pico cells are allowed to serve user concurrently. Okay, so multiple pico cells can work together to provide the solution. For example, if I consider this is my in the previous slide I told you 1 minus a zone where macro base station is active. Although pico stations are there, let's say their resources are not properly utilized. Means there is no that much load. So macro 1 and macro 2 are initially available up to 3 times less. Then let's say after this particular zone, then we will go for this particular zone, that is A zone. This is 1 minus A. These three slots are 1 minus A. Then let's say there is a A zone. So here the Pico base station can provide the services. The Pico base station means you can go for Pico 1, Pico 2, or you can go for Pico 3, Pico 4, or you can go for Pico 5, Pico 6, or any combination that is based upon the graph coloring protocol. For example, let's say this is a graph. So if you assign the node 1 with red color, then node 5 should be assigned with the red color only, because 2, 4, 3 cannot be assigned with the red color. If 2 is assigned with green color, 1, 3, 5, 4 cannot be assigned in green color. And if 3 is assigned with, let's say, this particular color, then 5, 2, 1 should not be assigned with that color. So based upon the same color, the Pico base stations are making pair. Like in this case, Pico 1 and Pico 5 is making pair, and Pico 2 and Pico 6 is making pair, and Pico 3 and Pico 4 is making pair. And there are some case all the Pico station can work together also. Okay, so there is 3 Pico operational mode here: 1, 5, 2, 6, and 3, 4. That means one can migrate with 2 and 3. If required, one can migrate with 2 and 3. Same color they cannot migrate. And 5 can migrate with 2, 3, 4, 6. Right? Because you can see 2, 3, 4, 6 are different color than 5. So now, similarly, 2 can migrate with, you can say 1, 3, 5, 4, because they are having different color, but it cannot be migrated with the 6. Whereas 6 can migrate with only 4 and 5, because they are adjacent to it. And if they are not adjacent also, you cannot migrate it. Okay. Like that, you can see the POM that allows all Pico stations to active simultaneously selected. Like you can see in a particular zone, all these nodes 1, 2, 3, 4, 5, 6 they are available. So we are selecting that particular POM. Now with this concept of signal aware technique, so we will see how to solve this particular problem. So what we are doing here in this case, so in signal aware algorithm, we are again making pair. Like fog node 1 is making pair with, I can say fog node 3, right? Because they are having the same color we can assign. And fog node 2 is having pair with fog node 4. So let us choose the first pair, that is FN1 and FN3. So in FN1, FN3, as they are in the same pair, FN1 can migrate to FN4 or it can be migrated to FN2. So if FN1 is migrating with FN2, so again there is two vehicles in the, these two vehicles are in the overlap region. If I take FN1 and FN2, right? So here, currently you can see it is 516 plus 421. So it is 937. Okay, 516 plus 421, that is 937. But after migration, okay, after migration, what you can do? You can see 516 is replaced with 315, and 327 is can be replaced by 421. Sorry, 421 is replaced by 327. So number of resource block reduction is same as DRO algorithm, which is 295. However, when you go for FN1 with FN4, currently it is 260 plus 682. So 260 plus 682, it is 942. Right? It is 942. So instead of 682, you can take 213 because number of resource block reduced is more. And instead of this 260, if you take 412, number of resource block is increasing. So you are not accepting this swapping, right? 260 to 412. However, you accept it 682 to 213. So what I can do, 682 is now replaced with 213, but I am keeping 260 as it is. So the number of resource block reduction, okay, required, it is 473. And number of resource block reduction is quite more here. So if you see, instead of in earlier case, if you see FN1 to FN4, okay, number of resource block reduction is 317, but now it is increased to 469 because before we are going to exchange anything, we are looking into that whether your current solution is better or not. Right? For that reason, you can see SA is performing better than the DRO algorithm. But when you go for fog node 3 with fog node 4, the performance is same, that is 248 in the case of SA as well as DRO algorithm. Similarly, when I go with for FN3 to FN4, So it is 130. Okay, and in this case also 130. So there is no significant improvement, I can say. Similarly, you can take the pair, the second pair, that is Fn2 is going to be migrated with Fn1. Okay. However, we already did the migration, so that you will not get any improved result. Similarly, I can choose Fn2 is going to migrate with Fn3, but already all migrations are done, so there is no further improvement. I can go with Fn4 with Fn1, Fn4 with Fn3, but all these migrations are done, so that's why there is no change in the result. So total number of resource block reduction, if I calculate here, because in this case we are considering all possible migrations. So here I am getting 295. Instead of 317, I am getting 469, and we are getting 248 here and 130 here. The total number of resource block reduction in this SA algorithm, it is 1142, right? So our objective is to maximize the total block reductions. So if you compare with the DRO algorithm, where the resource block reduction is 565, but now it is improved to 1142. So obviously, SA algorithm performs better than the DRO algorithm. Now what we are going to do, we are going to make a hybrid transition. Okay, like you found a better algorithm for one page, another algorithm for another page. So you are combining these two algorithms, right? So that we call it a DRO plus LC algorithm. So if you go for DRO SA algorithm, before migration, if I took for Fn1, Fn2, it is 516 plus 421. But after migration in DRO SA, first you will apply DRO. If you apply DRO, it will be take 327 and 315. And if you apply SA also, 327 plus 315. So the performance of this DRO SA is same as DRO and SA for this particular case. So that is 295. However, when we go for the exchange between Fn1 and Fn4, so before it is 260 plus 682, 260 plus 682, I am getting 942. Okay, so DR algorithm takes 213 plus 412. Okay, that is 625. But replacing 260 with 412 is not a good solution, right? So if you remember, in DRO algorithm, the number of resource block reduction is 370, right? Because that is between Fn1 and Fn4. But in this case, DRO plus SA algorithm, it is I am taking 260 plus 213, 260 plus 213. So it is 473, right? In the case of DRO SA. But when I compare with DRO and followed by DRO SA, the number of resources block reduction is increased. That is 621. Because in the first case, you have reduced it to 469, then you have reduced to another 152. Right, that is 412 minus 260, that is 152. So total reduction you are getting is 621. Similarly, you can go for Fn4 to Fn3. So there is only one vehicle. Okay, only one vehicle. Okay, so instead of taking 256, I am going to take 126. So resource block reduction is 130, which is same as DRO as well as SA algorithm separate. Now the last one, when we take Fn2 to Fn3, so the number of resource block reduction, you can see it is 248 like DRO and SA when we execute them separately. Yeah, if you see the total resource block reduction in this case, it is 295 plus 621 plus 248 plus 130, it is 1294. And if you compare with the individual DRO and SA algorithm, you can see in DRO algorithm, number of resource block reduction is 565, and SA algorithm it is increased to 1142, and DRO plus SA algorithm it is increased to 1294. So Fn1 and Fn4 case, if you look into Fn1 and Fn4 case, only we have seen there is a difference, right? But other cases, the performance of all these three algorithms are same. Okay, so in order to develop a new algorithm, you have to think about how to properly utilize these resource blocks, and where you can minimize the number of resource blocks, that is more important. Okay. Now there is another algorithm, which is the last algorithm, that is called as dynamic resource management algorithm. So in this algorithm, we represent the vehicles and fog nodes in the form of a matrix. Okay, we consider a set of vehicles and fog nodes in the form of a matrix. Okay, for example, you can see vehicle B1. Okay, vehicle B1 can be assigned to fog node 1, can be assigned to fog node 4, but this yellow indicates, sorry, orange color indicates that it is currently getting service from that particular fog node. That means it is currently getting service from FN4. Similarly, vehicle 2, it is getting currently, if you see, currently it is getting service from vehicle fog node 1. B2 is getting service from fog node 1. So it is represented in orange color. So the value is 551. Similarly, B3, B4, B5, B6 case, you can see the corresponding one. So if you see the sum of occupied resource block in this case, that is nothing but 433 plus 551 plus 328 plus 531 plus 200 plus 374. So you are going to get the sum of occupied resource block is 2417. Now, if you go for this particular algorithm, DRO algorithm, it says that choose a particular fog node. Let's say I am choosing the fog node is FN1 and the vehicle in its coverage area. So I am looking into what are the vehicles that are in the coverage area of fog node 1. So that is V1, V2 and V4. So I am only considering the vehicles that are in coverage region of FN1. So when I take a subpart, I can say submatrix of the whole matrix, then I apply the minimum algorithm. Min algorithm, this is a very famous algorithm, which says that in a particular matrix you have to find minimum of each row followed by minimum each column. Or when you apply mean in two different ways by finding row and column, then I can say it is the overall minimum. So you can see in the overall minimum here this 209. So that vehicle you need to process fast. Okay, that means B2 is going to be processed fast. And next you can see the overall minimum is 223. That means B4 is going to execute next. Then you can see B1 is going to process the next. So till now fog node 1's total number of occupied resource block is 292. Fog node 2 case it is 223 and fog node 4 case it is 209. And once these three vehicles are occupied, like V2, V4 and V1 is occupied, other vehicles we need to consider with respect to another fog node. Like if I take fog node 2, V3, V4, V5 are the coverage range of fog node 2, out of which V4 we have already assigned here. So that's why I represent it in the red color. Okay. And I'm finding again which one is minimum, whether V3 is minimum or V5 is minimum. So I am finding V3 is minimum because you can see there is no vehicle we have assigned to fog node 3. But there is a vehicle we have assigned to fog node 4. That is the reason, although it is minimum, but its cumulative is not minimum. Right? So fog node 3 has less resource block than fog node 4. So fog node 3 is going to be assigned with V3, followed by fog node 4 is assigned with vehicle 5. Okay. Now fog node 2 is completed. We'll go for fog node 3. Fog node 3 case, it has only two vehicles. One is V3 and another is V6. But V3 is already assigned here, so I am not going to consider that. I am only going to consider the V6 and the minimum we achieved in fog node 4. So we have to assign it in that fog node. Okay. So like that, if we process it, then we have seen earlier the sum of occupied resource block is 2417. But by using this DRM algorithm, the number of resource block is reduced to 1335. So we got a 44.76% of reduction in the case of DRM algorithm. Okay, so obviously it is better in comparison to if you compare with DRO algorithm or SA algorithm or combination of DRO and SA algorithm. So the process which we have adopted here is that DRM identifies the vehicles in the overlapped region. We are not considering the vehicles in the non-overlapped region. But we are considering the vehicles that are present in the overlapped region of the pairs of fog nodes and determine the number of resource block allocated to those vehicles from the fog node. And we are going to migrate the resource block from one fog node to another fog node. We are migrating the resource block of the vehicles, right? And we look into the number of resource blocks are reduced or not. If it is reduced, then we are going to accept it. So this is the algorithm. The input this algorithm is a network which we represent by this F, and we are taking a graph that is G of V, E, set of vertex and set of edges. And our objective is to get the output that is an optimal set of vehicles for the resource block migration and calculate 5 different parameters. One is service capability, serviceability, availability, throughput, and resource utilization efficiency. So I have taken a set of fog nodes here, and I initially considered that the set is 5 here. Then I am taking how many resource blocks are currently taken by all the fog nodes, and here I am taking each and every neighbor of fog nodes, and I am creating a set, okay, that contain overlapped coverage region of the parent fog node, overlapped coverage region of the both the fog nodes. Okay, then once you identify that, then we call a procedure that is called migrate resource blocks. In migrate resource block, we are finding the vehicles, minimum vehicles. Okay, the vehicles which are having very having less number of resource blocks, that we are determining here, and based upon that we are updating it. Because if a particular fog node getting more number of requests, then that may be overloaded. So in order to that, every time we are updating the remaining resource blocks. And this is the procedure to find the minimum. Initially, we consider a particular vehicle is minimum, and by looking into this number of resource blocks already occupied and currently required, we are calculating that how many resource blocks are required. Okay, what is the total number of resource blocks? By looking into that, you can determine whether to select a first fog node or the second fog node. Okay, so in this way we are performing the DRM algorithm, which I already shown you with an example. So that will be more helpful rather than this particular pseudocode. Okay, so these are the simulation parameters which we have considered. So we consider the number of fog nodes in a particular region is in between 10 to 50, and we consider that 10 vehicles are arriving to the network, whereas 5 vehicles are departing the network. That is, lambda is greater than the mu. And number of vehicles with respect to a particular simulation, we consider 2100 number of vehicles. And the network area where we observe this one is 1000 meter to the 1000 meter. And communication range in the single hop communication is 100 meter. And we used 3 different type of bandwidth in the fog net node, because based upon the bandwidth only we are going to calculate the resource blocks. So it is 10 megahertz, 15 megahertz, and 20 megahertz. And every fog node has a coverage radius. The coverage radius is 100 meter, and cumulative number of resource connection is 2100, and required data rate is 0.5 to 2. So the minimum data rate is 0.5, and we generated the data rate in the range of 0.5 to 2. So you can choose a data rate of 1.5 to something like that for each and every vehicle. And we consider the time slot duration is 1 second. We observe the scenario in 1 second, every 1 second, and the confidence interval we consider is 210 seconds. Yeah, this is the result you can get in the case of network service capability. So here you can see in the case of DRM algorithm, okay, DRM is represented with the dotted one. So you can see initially you can see its service capability is quite more, and it is getting services, it is providing services to various vehicles. So gradually it is decreasing. So after 200 time slots, you can see it is not able to provide services to any other node. But in comparison to DRM, if you go for DRO, SA, DRO, SA, and RO is random algorithm, you can see they are adjusting the network in a faster way. The network is fully adjusted, so they are not able to accommodate any other vehicles into the network. But DRM performs better in comparison to other algorithms. Similarly, if you compare it to service capability, it is providing better service capability in comparison to other node that you can see clearly. But other nodes are not performing. Other algorithms are not performing well. Similarly, we compared with network availability. So, in the case of DRM algorithm, initially the performance is not good. DRM algorithm performs better in terms of availability, but you can see after around 160 time slot, we observed that up to 210, the availability is better in the case of DRM algorithm. Similarly, when you go for throughput is increased in the case of proposed algorithm compared to another algorithm. We reached around 2200 Mbps of throughput using our simulation up to 210 second. Similarly, we compared with network resource utilization. You can see higher resource utilization leads that you cannot accommodate more requests. But if you look into DRM algorithm, it is having a good span from 60 to around I can say 95 or 96, something like that. But all other algorithms are fully exhausted, right? So DRM is still capable of receiving some other request from various vehicles. It can accommodate that vehicles and live in the network. And if you look at the resource block reductions also, resource block is also reduced in the case of the DRM algorithm compared to other algorithms. Although I have shown you an example, but if you see the number of resource block reduction up to 2100 vehicles, you can see it is reducing the number of vehicles in a better way. Okay, number of resource block reduction is more in comparison to any other algorithm. So, as a conclusion, I can say we have seen that the importance of 5G network and fog node, fog computing, cloud computing, IoT in this particular problem, and we solved two different problems. In the past problem, we have seen two algorithms. One is RRS algorithm, another is RBSM algorithm, and we observed that RBSM is performing better than the RRS algorithm. But another problem I showed you four algorithm DRO, SA, and DRO plus SA, which you can see DRM performs better than these algorithms. And if you want to simulate and if you want to observe the pattern, you can go for network analysis tools like you can take the data from a particular area using simulation of urban mobility and NS2 or NS3 simulator. And many people are also working on how to minimize the energy using artificial intelligence and machine learning models. And there is no standardized data set in this particular domain. So you can think about designing a real-time data set for this particular domain, which will help the research community to execute the simulation. Okay. So these are the some of the aspects which we have discussed in this lecture. And these are some of the publications where in this respective domain. If you are interested, you can go through these publications by my team so that you will get more details about this area. And these are the references. If you are interested, you can go through these references. Yeah, thank you everyone. If you have any question, you can